Good evening, everyone. Today we will start with the new topic, circular dichroism spectroscopy. Over here, this spectroscopy is a kind of absorption spectroscopy. Okay, so in absorption spectroscopy, what we are having? We were having a light source, right? Then we are having some excitation optics. Then we are having a monochromator. Then we are having sample. Then at the end we are having detector. Okay, and in between we could have some other kind of optics were also there. If we need, we can have this transmission optics, or this is excitation optics and transmission optics. Okay, and then we have this detector. Okay, this was the thing. So herein what we were looking over here, we were looking into the that the radiations, they were being generated by the source. They were being then collimated and condensed by the excitation optics. Then we used a monochromator light to make a monochromatic light incident onto the sample, and outside of through this sample, when this monochromatic light passed, what we were having that some of the incident rays were being absorbed by the sample, and we used to get the transmitted radiation. Okay, IT. So herein we were having I0, and herein this I0, it was equal to I transmitted plus I absorption. So the amount of, or the intensity of the light which was being absorbed by the sample, and the light which is being transmitted through the sample, and we were detecting this IT. Okay, and we were also having this I0 component, and by the ratio of this one, we were getting the absorption. Okay, by having this I0 and IT values, we were getting the absorption values. Now this circular dichroism spectroscopy, in short, it is also regarded as CD spectroscopy. Okay, it is also regarded as CD spectroscopy. Okay, however, in this type of spectroscopy, we do not go for the measurement of the certain compounds. Okay, we cannot go for measurement of compounds. Measurement of concentration of compounds. Sorry, concentration of compounds. So what we do over here, we basically look into the secondary structure of the proteins. Sorry, secondary structure of proteins. So CD spectroscopy, it helps us in understanding the secondary structure of the proteins. Okay, and already as I told you, the CD spectroscopy, it is a variant of the absorption spectroscopy. So you will find that when we look into the absorption, this CD spectroscopy, spectroscopic system, we will find that there are subtle variations in this architecture. Overall, this would be the overall architecture. However, there will be subtle variations over there, and due to that subtle variation, we are able to get information about the secondary structures of the protein. Okay. Now background. So as I told you, it is basically an absorption spectroscopic. Okay. So in the second case, over here, we have this word dichroism. So what is dichroism? So over here, a dichroic material is a material that can split up visible light into beams of different wavelengths or different polarizations. Okay, so a dichroic material is a material that has the capability for splitting up the visible light into beams of different wavelengths or different polarizations. In our study over here in circular dichroism, we are mainly interested in materials which can split up the visible light into different polarizations. Okay, so circular dichroism is the dichroism that involve circularly polarized lights. So in short, it is called CPL. Okay. Now, when it is called circularly polarized light, so if you look into a circular, so we can either go into the clockwise direction or into the anti-clockwise direction. So the anti-clockwise direction, that if the polarized light is being circularized in the anti-clockwise direction, then it is called left circularly polarized light. If your polarized light is being moved into the clockwise direction, then it is called the right circularly polarized light. Okay. So in this case, in CD spectroscopy, it basically deals with the differential absorption of left and right handed circularly polarized light. Okay. So all these molecules, these proteins, they have the capability to differentially absorb either the LCPL or the RCPL lights. Okay. So from here, as I already told you, we get the structural information of the proteins. Okay, we get the structural information of the proteins, and we are able to predict the secondary structure, and also it is possible to understand whether there is a protein folding or unfolding due to the changes in the environment. Say for example, you have had some analyte and you want to see whether that analyte can change the folding pattern of the protein. So which instrument you will be using? You have to use the CD spectroscopy. Okay. Suppose there is a change in the pH of the protein solution, whether there is any change in the secondary structure or protein folding. Again, you have to use the CD spectroscopy. Okay. Now, before moving forward to the linearly polarized light, we need to understand that the visible lights, they are transverse waves. That means what you have, you if you see the light waves, they move in a sinusoidal wave in the direction of the propagation. So I am marking it the direction of the propagation in this axis, so which is basically the x-axis. I am marking it as P. Now we all know these visible lights, they are nothing but electromagnetic radiation. However, these electromagnetic radiations, they are not only dependent on the electrical field, as the name over here what I have shown you, this is the this sinusoidal wave, this corresponds to the electrical field. it is also associated with a magnetic field, which is perpendicular to this electrical field. Accordingly, we say that the electromagnetic fields or the visible light waves, they are transverse waves. And when we talk about this, suppose we have a bulb through which the radiation are being generated. So what happens over here? In this case, the light are being moved in all this direction. Okay. Now when we so we are having this suppose we are having this say if we just consider the, because over here as I told you, we are having electromagnetic radiation, we are having electric beam, we are having magnetic beam, and both are in perpendicular to each other. However, what happens, the um, electric field or the intensity of the electric field, it is much higher than the magnetic field. And usually when we talk about this propagation of this visible light, we usually tend to tell them, or we tend to regard them only with the electrical field. So herein, if you see, as I told you that the electrical field, it moves in the sinusoidal wave. Now from this direction, from the opposite side of this propagation direction, if you see, you will be seeing that from the basal level, which is the zero level, the amplitude is increasing and also the amplitude is decreasing. So usually this propagation of the light, it is shown in this way. So in between there is a 0 point and it moves upwards and downwards. However, what happens is that, as I showed you over here, the light are being propagated, the light beams are being propagated in all the directions. So if we compile this and if we show this over here, supposing that at this point we have a point source, so what we have, we will be getting different radiations like this. Will in another direction we will be having another beam. In another direction we will be having another beam, so on. Okay. So this is somewhat is the nature of an unpolarized light. This is somewhat is the nature of the unpolarized light. Now when this unpolarized light, it is being passed through a material which has the capability to modulate this unpolarized light such that only the light beam having polarization in a particular direction, it is being passed through. So that material, it is called polarizer. Okay. Now if you see the output of this polarizer, it would be like this. So you will be getting light beams which are having electrical modulations only in one direction. Okay. So if you see over here, so what is happening? Initially we are getting the unpolarized light where the electrical field of that light was in all the direction. However, by employing this polarizer, we are only allowing the light to pass through the polarizer which are varying only in one direction. Say for example, in the y direction, the electrical field, it is being varied. Okay. Now from here, can you tell me the first difference between the UV visible spectroscopy and the this CD spectroscopy? What should be the difference? Main difference? The main difference would be, if you see, a majority of the light are being rejected. Majority of the light beams are being rejected. Okay, so herein the source of the light should have a high intensity or should generate high intensity beam. Am I clear? So this is called a linearly polarized light. Okay. Then we have circularly polarized light. So in the circular polarized light, if you see in the linear polarized light, the variation in the electric field, it was only in the Y domain. Whereas in the circularly polarized light, if you see in the direction of the propagation is this K direction, and then you are having this electric beam which is being moving all throughout this, and the radiation this radius of all this what you call these rays, they are having the same thing and they are moving in a circular way and they are moving in a particular direction. In this case, if you see in the linearly polarized light, at different instances you are having different magnitude of the electrical field. Okay, so you will find it will start with 0, it will attain a maximum, it will again this intensity, it would come down to to a minimum level, then again it will rise to 0 and again to the maximum point, and again it will come down to the minimum point through this by crossing over to the 0 level, and so on. So in this way it is going. So in linearly polarized light, the intensity of the electrical field, it continuously changes over that period of time, whereas in the circularly polarized light, the intensity level, it remains the same. However, over here, when we talk about this movement, it is moving in a helical pattern. It is taking a helical path. Now, in this case, this helix, it may be a right-handed, sorry, it may be the right-handed helix, or it may be the left-handed helix. Okay. So what over here in the right-handed helix, this beam, it will be moving in a right-handed direction, whereas in the left-handed helix, the direction of the movement of the beam, it would be towards the left hand side. Okay, so in the left hand helix, it would be something like this. So it is moving in the anti-clockwise manner. See, I have moving this my cursor in the anti-clockwise manner. So that would be the left handed helix, and hence this light would be called left circularly polarized light, LCPL. CPL. On the other hand, if it would have been moved into the clockwise direction, so the propagation of the light would have been in this fashion, in the right-handed helical manner. Then it would have been called right-handedly right-handed circularly polarized light, or CPL. I hope up to this point it is clear to all of you. Okay. So if you see over here, linearly, or it is also called plane polarized light. Over here, if you see the amplitude of these values, they are varying. Not only the amplitude, also the direction. Okay. So please correct me in the whatever I have told in the previous slide. This amplitude and direction, both are changing. However, in the circularly polarized light, what is happening? If you see, the amplitude remains same, only the direction changes. Okay. Again, if you see left-handed circular light in the electrical vector, it would move in the anti-clockwise direction, whereas the right-handed circular light, it would be moving towards the clockwise direction, and it would look something like this. The electric field vector, it would look something like this. So we will be having the right circularly polarized light. Okay. So if you see, it is moving in the clockwise direction. See, it is moving in the overall electrical field, it is moving in the clockwise direction, right? So apologies for the bad tracing of the waves. Okay. So I hope up till now it is clear to all of you that what is right-handed circularly polarized light and what are left-handed circularly polarized light. Now, before we move forward, so we need to understand what is the difference between this UV rays absorption and the electronic circular dichroism spectra of different compounds. If you see herein, the structure of camphor has been given. Okay, so the chemical structure of both of the uh, plus camphor and the minus camphor, plus means dextrorotatory and minus means levorotatory camphor. In the case of UV visible spectroscopy, they would be the same. Okay. However, what we see, this dextrorotatory camphor and the levorotatory camphor, they are nothing but enantiomers. Okay. And since both of them they are giving you similar pattern, it would be next to impossible to identify whether you have been given with this dextrorotatory camphor or levorotatory camphor. So this was one of the disadvantages of the UV visible spectrometer. Are you getting my point? This is one of the disadvantages of the UV visible spectrometer. Now, what is the way out? The way out is the circular electronic circular dichroism spectra, wherein you can have this dextrorotatory camphor and the levorotatory camphor, which are having different absorption profiles. Okay. Now, if you see, there is another important point to notice over here. Herein, we are talking about eta. What is eta? Can anyone tell me what is eta? We have already discussed in UV visible spectroscopy class. What is eta? Anyone? अरे पता है नहीं पता है कुछ तो बोलो.
Sir, is it same as epsilon, extinction coefficient or molar absorption coefficient?
Exactly. It is this eta. It is nothing but your molar absorption coefficient. Okay. However, in the case of this circular dichroism spectra, if you see, we are using delta eta or delta epsilon, whatever you call. Okay. So let us call it as epsilon, as most of you are more conversant with this epsilon term. So it is delta epsilon. So what is this delta? So I talked about this right-handed circularly polarized light, and I talked about left-handed circularly polarized light. So we are having two types of radiations. So in electronic circular dichroism, what we do is that we individually find out the absorption due to absorption of the RCPL by the sample and the absorption of LCPL by the sample. Okay, so in the case of enantiomers, where there are different chemical orientation but the chemical formula remains the same, in those cases it has been seen that they would rather absorb either the RCPL or the LCPL more, and the other may not be hampered or may not be absorbed to that greater extent. Okay. So what I mean to say, so in say sample A, if it is having an enantiomer, so it may absorb RCPL higher as compared to the LCPL or vice versa. Okay. So due to this reason, due to the differential absorption, what we are looking over here, we are looking into the delta E. Okay. So this delta E or delta epsilon, sorry, delta epsilon, it is giving us the information about the dextrorotatory or the levorotatory nature of the compound. Okay. So this enantiomers, what are they? So one of the important thing what you need to remember is that when you are talking about the circular dichroism or circular dichroism spectroscopy, you need to remember that the sample should be optically active. If they are not optically active, it will be difficult for you to get this delta epsilon. Okay, so optically active, what compounds are optically active? If they are asymmetrical, if they have chiral centers, and if they are enantiomers. Okay, so what is a chiral molecule? A chiral molecule has a non-superimposable mirror image. Okay, so what is dextrorotatory? Dextrorotatory is nothing but right-handed movement of the electrical field, that means the clockwise. So this lead to the generation of the right linearly polarized light. Okay, and many of the compounds like sugars and carbohydrates, they are inherently dextrorotatory in nature. On the contrary, levorotatory, they move the polarized light into the in the left-handed movement way. That means in the anti-clockwise manner, and they lead to the generation of the left linearly polarized light. And usually these are being shown by the phospholipids and the proteins. Okay. So herein we have another parameter over here, optical rotatory dispersion. Optical rotatory dispersion, which can be studied using a spectropolarimeter. Okay, so what does this spectropolarimeter do? It measures the ability of the optically active compound to rotate the molecules in either clockwise or anti-clockwise direction. rotate them, it will not be the molecules, it will be the electrical field, sorry. To either to the clockwise or the anti-clockwise direction. So here I have used another important parameter which is different from CD spectroscopy in fact. So herein you are having the radiation source, then you will be having the optics. I am not drawing those optics. Okay, excitation optics would be there. Then you have the samples. So if you say okay, optics, let us okay. Then yeah, again over here we will be having the polarizer. Then we will be having the sample. Now over here we will be having the detector. Okay. Now this detector, what it does is that it detects the changes, whether the light has been moved in a clockwise direction or in the anti-clockwise direction. Okay. So how you do this? You do this by inserting another polarizer, but we not call it as polarizer, we call it as analyzer. We call it as analyzer. Okay. So what it will do is that when you have this sugar or the say sugar or carbohydrates. So initially you were having this light beam which was passing through the optics through the polarizer. You got this polarizing beam over here and it was passing through over here. However, the sugars and the carbohydrates, what they would do? They would move the orientation of this electrical field by a certain degree towards the right. Right? Now, when it comes over here in at this analyzer, if this light beam, if it is not parallel to this to the orientation of this analyzer, which is again a polarizer basically, but since we are using it for the analysis of the light beam, so because of this reason we call it this thing, we call it analyzer because we are using it for the analysis purpose. So we have to rotate this analyzer by a certain extent so that the intensity level it becomes the highest over here. Okay. So what is happening? So when this light it becomes this polarizer orientation of this analyzer, it becomes parallel to the orientation of the light beam which is being passing through. Then you tell it that if you have to move it towards your right, then it is a dextro-rotatory movement, and you can say that your sample which has been provided in the cuvette, it is a dextro-rotatory sample. And if you have to move the analyzer towards your left hand side to get the maximum light information, then it is called the levorotatory sample. So this we do it in the optical rotatory dispersion spectroscopy, or we also call it spectropolarimeter. Okay, in the spectropolarimeter we do like this. Okay, am I clear? Because until and unless you have not understood this spectropolarimeter, it will be difficult for you to understand the CD spectroscopy. Since I am not having any questions from you, I am moving forward. So, what happens over here in the CD spectroscopy? We have a high intensity light source. Then we have the excitation optics. In this excitation optics, we have the polarizer inbuilt. Okay. So what is this polarizer? What do you mean by polarizer is inbuilt in? This means you are having these lenses, then collimating system and whatever you say. And in addition to that, you have the polarizer also over here. Okay. So from the source, you are having this collimating system and monochromator and all these things. And within that excitation optics, you are also having the polarizer. So over here, after this M, you are getting polarized light, linearly polarized light. Okay, you have to keep this in mind. Then after that, once you have this linearly polarized light, you have PEM. What is PEM? PEM photoelastic modulator. PEM is photoelastic modulator. So in the previous case, herein we are having the sugars and carbohydrates which were moving the light in the dextrorotatory fashion, or phospholipids and proteins which were moving the light in the levorotatory manner. In this case, we have this PEM, and this PEM does the same thing. It either moves this linearly polarized light in a dextrorotatory fashion or in a levorotatory fashion. Now, herein there are two types of PEM. This is the first one. We are having the first one. We are having, maybe say it will generate left-handed circularly polarized light, and the second PM, it would be generating the right-handed circularly polarized light. So this one, this PEM and this PMT, they are being synchronized. They are being synchronized using the computer program. Okay. So what it does, this computer program, it moves this PM crystal into the path of the light in a, what do you call, in a reciprocal manner, reciprocal, or say oscillating manner. So at one instance, it would be the second crystal would be in the path of the light. In the second instance, you will be having the first crystal over there, and again it would repeat. So there is a movement of this crystal in this fashion, so that alternatively the crystal 1 and crystal 2, they come in the path of the radiation. And this computer program, it will also send the information to the PMT. So whatever the signal it is being acquiring, it will acquire the same in the computer program, and it would keep it that this is for the, this reading is for the RCPL, and the say when the second crystal is in the path, then it would say that whatever the information it is getting from the PMT, it will keep in mind, or it will keep it in volatile memory, that we have got the information from the RCPL, and in the other instance the reading is from the LCPL. Okay, so in this way it would record both the readings, RCPL and LCPL readings. Okay, so after the linearly polarized light, it passes through PEM. If you see, we are getting the circularly polarized light. And how it is there? We are getting an alternating burst of left and right circularly polarized light. And then we are having the sample. And in this case, we are having the sample, it is absorbing the circularly polarized light LCPL and RCPL in a differential manner. So one would be absorbed get greater than the other one. Okay, and that difference in the absorption of RCPL and ACPL, so sorry, LCPL. So if you see, in one case it will be higher, or in the other case the other one will be higher. So there will be a change in the absorption pattern by the sample. Okay. So you have to keep in mind another, I want to make it sure, in the spectropolarimeter, the sample was changing the orientation of the polarized light. You have to keep in mind. In spectropolarimeter, the sample was changing the orientation of the polarized light, whereas in CD spectroscopy, sample is not changing the orientation. What it is doing, it is just absorbing the light either in the absorbing the light in a differential manner depending upon their structure. Okay, in a differential way. So this is the difference. So there are certain polarizer materials, and these polarizer materials include nickel prism, Gland Thomson prism, and tourmaline crystal. Among these Gland Thomson prism, they are very commonly used as a polarizer because they have this Gland Thomson polarizer, this Gland Thomson prism, they can be obtained in more pure form. Okay, this is the thing. So again, if you see the same thing, just to show you in a much more better manner, you have the light intensity, this light source, which are unpolarized light. Then you have the monochromator and the linear polarizer, and accordingly you will also have the wavelength selector over here. Then monochromatic light is being generated. Then you have this PEM. In this PEM you generate a burst of linearly circular polarized light and right polarized light. So it will be passing through the CD active sample, and then it will be absorbed by the detector. And the movement of this PEM, it occurs at 50 kilohertz. Okay, and this detector, it gathers the signal and it finds out the difference between the RCP and LCP. So the speeds between the right and the left polarization differ. CL is not equal to CR when they pass through the samples. The sample wavelength, the wavelength lambda L is not equal to lambda R, and the extent of absorption, molar extinction coefficient, epsilon L is not equal to epsilon R of the polarized lights. Okay. Circular dichroism spectroscopy calculates the difference in the molar absorption. Okay. Delta epsilon is equal to epsilon L minus epsilon R, and it is also called molar circular dichroism. This delta epsilon, it is called molar circular dichroism. The series spectrum is often reported in degrees of ellipticity, which is a measure of the ellipticity of the polarization. Okay, so what happens is that if you see from the direction of the in the opposite direction of the polar this what do you call propagation, if you see from here, you will be looking into this um, RCL or RCPL, that if you look into from this area, from the right hand side, you will find that it is having a circle. So same, you are having this one, blue one is ER, electric field of the right circularly polarized light, and this red one, it is for the EL, electric field of the mm, left circularly polarized light. Now, what are these? These are nothing but the electrical vectors. One is moving towards your right. So let me draw separately. So the red one is electric field of the left circularly polarized light, and the blue one is for the ER. Okay. Now I am showing you both the field. ER, it is moving right. Suppose it is in this position, and the other one, oh sorry, the other one is in this position. Okay. Initially it was okay. Initially, let's start from the zero position. So in the zero position, both are in the same direction. So what will be having? Both will be added up. It will be at this point. Similarly, if you look into the this 6 point of the clock, so six number of the plot. So over here at a 6 o'clock position or 6:30 position, what will happen? Both of this will be in the downward direction. So again, they will be added up. Okay. And then at the 3 o'clock and the 9 o'clock position, what will happen? The RCPL, it is moving in the right direction, and the EL, it is moving on the left direction in the anti-clockwise manner. So what will happen in both these stages? In suppose in the first case, in if you consider the ER, so ER will be like this at the 3 o'clock position, and they will be the other one, the LCPL, it will be on the opposite direction. So there will be a net difference, right? Similarly, on the other side also, at a 9 o'clock position also, you will be having the same thing. So the net electrical vector, it would be smaller as compared to the positions in 12 o'clock and 6 o'clock positions. So at these two positions, we will be having higher electrical vectors, and at the 3 and 9 positions, we will be having smaller vectors. So if we join these, considering that it is being moving in all these things, so it is forming an ellipse, and hence the name comes ellipticity. So degree of ellipticity means, if you see over here, if you plot a right angle over here, so this theta, it is called the degree of ellipticity. It is basically, it is giving you information about the how much is the added form of a added electrical vector intensity, and the what is the minimum what you call diameter, higher diameter and the lower diameter. Okay. So over here you find out the intensity, the high intensity and the low intensity value. And how we are finding out? We are finding out by calculating this theta here. So hence this theta, it is regarded as the degree of ellipticity. Okay. And this is what it is being written over here. Electrically polarized light, purple, is the superposition of LCP and RCP light. Theta is the angle between the magnitude of the electrical field vector at its maximum and its minimum. Okay. So what is this theta giving you information? It is giving you information about the measure of the ellipticity of the polarization. Okay. Now this theta, as I told you, it is being given by 2.303 by 4 AL minus AR. What is AL? Absorption of the left circularly polarized light minus absorption of the right circularly polarized light. Now theta can be converted to degrees. This is in radians. It can be converted to degrees by multiplying this delta A with 32.98. Okay. So the molar ellipticity, um, it can also be regarded as this delta theta is equal to 3298 multiplied by delta epsilon. Okay, delta epsilon. So 3298 multiplied by delta epsilon, and this is what we have seen, that we convert it into delta epsilon. We do not look into the delta A, whether, because delta A, this delta is the absorption. A is basically the absorption, how much light is being absorbed, whereas epsilon, it is an inherent property of the sample. So if you see, absorption is equal to epsilon BC. Now when we talk about this, what is A? A is a combination of epsilon, B and C. B is the path length and C is the concentration. However, this B and C, they are constant for a particular experiment. Okay, and what we get is basically this epsilon, which is the inherent property of the sample. So in majority of the cases, you will find this molar ellipticity. It is being reported. Okay. And this is what it is being told, which removes the dependence on the concentration and the path length. Okay. So the final thing is that what does it, what information does it give? If you see, if you find out the wavelength dependent this molar ellipticity, so you will find that you will be getting certain curves. So this red curve is for the alpha helix, and in the alpha helix you will be having three peaks, one at 190, uh, which is a positive peak, and there will be two peaks at 208 and 222 at negative peaks. So this peak is at 190, and there will be two peaks at 208 and 222. So this would be the nature of the alpha helix proteins. Okay, then you can have the beta sheet. In the beta sheet, this green color curve, it is being given by beta sheet. So you will be having 196 and 218 nanometer. You will be having two peaks. One is the positive peak and the other is the negative peak. And then for the random coil, you will be getting this kind these two peaks. So first is the negative peak and the second is the positive peak. Okay, now in the real case scenario, what you do, you have to, from this pattern you have to find out what kind of uh, proteins or what kind of secondary structure proteins are present. Say for example myoglobin, which is having all alpha. If you see, the first one is the myoglobin. Over here you are getting the all alpha peak, and it would correlate extensively with the alpha helix form. Okay, in the case of the lysozyme, you will be having mixed alpha and beta, and the red one is the lysozyme. So if you see the nature of the curve, it has changed to a combination of alpha and beta structures, something like that. This red one. Okay, and then we have this uh, triphosphate isomerase enzyme. So this triphosphate isomerase enzyme, it is having mostly alpha and some beta. So if you see, since it is mostly alpha, it is giving, if you average these alpha and beta components, then it will be giving you a curve similar to alpha. More, it will be more tending towards the alpha, and hence you get something like this. And lastly, you get the chromotipsin, where you have all beta. So over here you are having the all beta, and it would give you information about the beta sheets over here. So in this way you use this. However, we do not use uh, this CD spectroscopy for what you call for this concentration calculation. Mainly we use it for the this for identifying the secondary structure of the proteins. Okay, so with this I complete the chapter.